Hi, my name is Daniel, and welcome to this presentation on Service-Level Objective-Aware Neural Networks, or SLONNs. To give you an overview of what we'll be talking about in the next few minutes, first I'll talk about inference serving systems and the challenges that they need to overcome, and then I'll describe the drawbacks of existing methods. Next, I'll describe our proposed SLONN approach and show some preliminary results. Finally, I'll conclude with some ongoing research directions. So what is an inference serving system? In an inference serving system, users send inference queries to a managed cluster of worker machines, which are hosting trained machine learning models. So what is an inference query? An inference query includes some input data, for example, an image, as well as some service level objectives, or SLOs. SLOs typically include a latency constraint and an accuracy requirement. And so the role of the inference serving system is to select a model that best fits and serves the SLOs of each query. So let's get into some of the challenges that inference serving systems face. The first of which is SLO diversity. SLOs vary widely within and across inference application domains. To give an example of this, consider a situation in which a social media application, a visual guidance application, and an intruder detection application all query the same image classification system. The difficulty is that the social media application requires high accuracy but medium latency, while in contrast to the intruder detection application, which has a low accuracy constraint but a low latency requirement. On top of this, those SLOs may evolve over time. And therefore, inference serving systems must be able to handle situations in which each query may differ in SLOs. Another challenge that inference serving systems face is collocation interference. What collocation is when multiple models are placed on the same worker machine. The reason why we might do this is that it improves hardware utilization, which in turn can reduce cost. However, there's the potential that the inference latency of the models will slow down due to interference from resource contention. Still, inference serving systems must handle situations in which collocation interference can cause slowdown so that they can make decisions that avoid SLO violations. Another difficulty that inference serving systems face is the fact that query load is often volatile. So the fluctuation of query rates can incur varying queuing delays and also can cause intermittent latency degradation from collocation interference, where collocated models exhibit fluctuating query rates. Still, inference serving systems need to handle these situations where query load is dynamic while still meeting SLOs. So how do existing inference serving systems address the challenges we've previously discussed? So as we've seen before, inference serving systems generally employ the approach where for each query, they will select the model that best fits the SLO. Example systems which employ this approach include Clipper, InFAS, and Alert. Clipper proposed an adaptive model selection, while InFAS expanded on the notion of adaptive model selection to minimize cost, while Alert expanded adaptive model selection to optimize energy consumption. The drawback of these approaches is that these systems are burdened by managing and training many models. So now let's talk about our proposed approach, Service Level Objective Aware Neural Networks, or SLONNs. So in contrast to the existing solution to those challenges where we require training and managing many models, to address the challenge of diverse and evolving SLOs, our proposal is that we use one model which is capable of serving a variety of SLOs. Further, for the challenges posed by potential SLO violations from intermittent collocation interference and varying query load, we propose using a model which can dynamically adapt to computation to avoid SLO violations. We note that this technique that we're proposing has no restrictions on how the model is trained, where the user can provide a trained model and we add the dynamic facilities to enable these features. So we need a mechanism in which we can adapt computation at inference. So we leverage the fact that in neural networks with ReLU activation, intermediate activations are often sparse. So to convince you of this fact, here I'm showing the intermediate activation of a 3-layer neural network on FMNIST. The y-axis exemplifies different input examples to the neural network, while the x-axis exemplifies the differing activation of each node in the second layer of the neural network. What you'll notice is that the activation is quite sparse. Further, the activations that end up being 0 have no impact on the inference result. Thus, we can reduce latency by omitting computations that are likely to end up being 0. So the specific mechanism that we use, which is capable of adapting computation at inference, we place a node activator at each layer of the network. The node activator will rank nodes by importance and select the top K% at inference. Here, I'm illustrating the approach. The node activator takes as input the input to the current layer, the SLO, and the current worker utilization in order to determine how many and which nodes to activate in the layer. As we've stated previously, the node activator activates the top K% at inference. So the K depends upon a user-specified optimization objective. Either the user desires to minimize latency given an accuracy constraint, or maximize accuracy given a latency requirement. So let's talk a little bit about the specifics of the node ranking mechanism. So the node ranking mechanism exploits the fact that similar inputs to the layer exhibit similar activation. We chose locality-sensitive hashing to rank node importance. The reason for this choice is that locality-sensitive hashing exhibits extremely low overhead. And so what this will look like internally within the node activator is that at each layer, we're going to hash the input to the layer, and then use that hash to index into a table, which we then, from that table, we will retrieve a node importance list, which contains a list of node indices sorted by importance. So now that we've talked a little bit about the node ranking mechanism, let's talk about how we determine K. Again, K is the percentage of nodes that we're going to activate at each layer. So K depends upon the optimization objective that's specified by the user. For minimizing latency, giving an accuracy constraint, we use confidence to determine K, where we minimize K such that we're still confident that the inference will be accurate enough to meet the accuracy SLO. Confidence is estimated again by locality-sensitive hash, where we exploit the insight that similar inputs exhibit similar confidences. What this looks like internally within the node activator is that at each layer, we're going to take the input to the layer and hash that using a locality-sensitive hash. And then we're going to determine K by indexing into a confidence locality-sensitive hash table, which will have a mapping between a hash to a K. Then we will take that hash and use it to index into the node importance locality sensitive hash table, which will provide us with the node list importances. Finally, we then use the selected K and the node importance list to determine which nodes to activate within the layer. On the flip side, when the user desires to maximize accuracy given a latency constraint, the node activator will instead use a latency profile to determine K. The latency profile will be used by the node activator to determine what is the latency of the layer given K and the current machine utilization. The node activator will select K such that the projected latency will satisfy the latency SLO, and will then choose nodes according to the selected node importance list. So let's briefly discuss a comparison between SLONNs and existing dynamic neural network approaches. So there has been prior work which has proposed conditional computations for neural networks. However, the techniques that have been proposed exhibit limitations which are not faced by SLONNs. First, these existing techniques place restrictions on the model architecture or training procedure. Further, they may not achieve state-of-the-art accuracy. And finally, SLOs for these techniques must be expressed prior to training the model. Each of these limitations are not exhibited by SLONNs because the auxiliary facilities of SLONNs is added in post-training or post-deployment of the model. We'd like to highlight the difference between SLONNs and static model pruning approaches. So, static model pruning involves permanently removing weights and neurons, which is different from SLONNs, where we dynamically prune neurons, but neurons are never permanently removed from the neural network. In our evaluation, we actually applied static neuron pruning to the original neural network before transforming the neural network into an SLONN. So we'd like to note that SLONNs and static optimizations, such as model pruning, are complementary. So if you'd like to know more about the details of the node activator, please read the paper. But for now, let me demonstrate some preliminary results we had in experimentation with SLONNs. So in the situation where the optimization is to minimize latency given an accuracy constraint for each query, here I'm showing the accuracy versus speedup plots for two different datasets, FMA and Amazon K13K. The dotted black line exemplifies the accuracy of the full neural network, while the red lines exemplify the accuracy versus speedup against the full neural network. The solid red line exemplifies the mean behavior, while the red dotted lines exemplify the min and maximum. What we can see from this plot is that for these two data sets, SLONNs achieve average speedups of up to 1.3 to 2.1x with little to no accuracy loss. Further, we can observe that they're able to serve a range of accuracy and latencies with one model. Now let's discuss the results for which the optimization objective was to maximize accuracy given a latency constraint. Here I'm showing the accuracy versus latency plots of two datasets. The black dashed lines exemplify the performance of the full neural network in isolation, while the purple dashed lines exemplify the performance of the neural network when it's co-located. The blue and yellow solid lines exemplify the performance of the SLO-NN when it's isolated and collocated, respectively. What we can observe is that even when collocated, the SLO-NN is able to reduce computation such that it lowers latency, however, it maximizes accuracy. And this exemplifies that SLO-NNs can adapt to meet SLOs under collocation interference while minimizing accuracy loss. So now let me briefly describe some of the ongoing research directions we plan to pursue. Thus far, we've only experimented with multi-layer perceptron neural networks, and we plan to evaluate our technique on other types of neural networks, such as convolutional neural networks and transformers. Further, we plan to evaluate our technique on batch inference workloads, where thus far we've only experimented with online inference batch size 1 workloads. Further, we plan to explore other node ranking mechanisms beyond locality-sensitive hashing. And finally, we're interested in looking into how online updates to the node activator can improve the node ranking quality. So that concludes my talk. Thank you for listening.